Hello and welcome to this FMSP online revision session looking at the MEI D2 specification. Today's topic is going to be networks, and so let's have a look at first of all at what you need to know. So you need to be able to solve route inspection problems. Those are the ones where you have to travel along every edge at least once and return to the starting point, in other words to find an Eulerian cycle. You have to know how to solve travelling salesperson problems, and travelling salesperson is the one where you visit every vertex and return to the starting point. This is an interesting problem mathematically because we don't have a way of solving it, so there's quite a lot of modelling involved. You have to be able to convert the practical problem into the classical problem, and this involves creating a complete network of shortest distances. Once you've done that, you solve the problem. You will then get an answer which you have to be able to interpret in the light of the original problem that was set. And in order to get your answer, there are two algorithms, one for upper bounds and one for lower bounds, which you need to know. And the third topic on the network section is Floyd's algorithm, which extends the ideas from D1, where you did Dijkstra, and to being able to find the shortest distance between any two vertices in a network. So most of the questions are quite long, and that's largely because they are a lot of topics to be examined. So this particular question here had 20 marks associated with it, so it's going to take you around about 20 minutes to do a question like this. So you can see that there's a lot to read. Let's start with the first part. So you're given the network and you're asked to set up the initial matrices for Floyd's algorithm. And the initial two matrices, on this side you have a distance matrix, and on this side you have a route matrix. And the easiest place to start is with the route matrix, because all the route matrix does is assume that you are starting at whichever vertex you are standing at, and so you just fill in the columns with the numbers like this. Now once you've done that, you need to fill in the distances from the network, and this particular network created problems when it was in the exam because of this point here where I've just put a little dot. That is not a vertex. There is no vertex shown there. If 1, 2, 5 and 4 are cities, you can think of that as being a crossroads. So first of all, any vertex doesn't have a direct route to itself. So we put infinity in 1, 1, 2, 2, 3, 3, 4, 4 and so on. And then looking at vertex 1, if we go from 1 to 2, we are going all the way along here, and so the distance is 7 plus 15, which is 22. And that was the thing that a lot of people didn't get, sadly. 1 to 3 does not have a direct route, so again we'll put an infinity in there. We use infinity because we don't want these things to crop up in any initial solution that we have, and infinity is just a way of saying it's a very long way. 1 to 4, again you've got a problem with your crossroads here, so you go 7 along up to the crossroads and then 8 down, so that's a distance of 15. And finally 1 to 5, you might assume it was 20 because that's the direct route, but if you go the other way you can go along for 7 and down for 8, giving you another 15. That was tricky. A lot of people made errors with that row of the table. Once you've got the top row, you can actually fill in the column because these things are always symmetric. So we can save ourselves a little bit of time by realizing that and just filling in column 1 as well, and then move to vertex 2. So 2 to 3 is a direct route of 20. 2 to 4 is a direct route of 5. And 2 to 5 is also a direct route, which is 15 plus 8, which is 23. And again, I'm just going to fill in the column to make it symmetric. Then looking at vertex 3, 3 has a direct link to vertex 4, which has a distance of 40, and there's no direct link to vertex 5, so we'll put our little infinity in there. And finally 5 to 4, starting at 4 going up to our crossroads and down to 5 again, is a distance of 16. So we've completed our initial matrices. There was 1 mark for the root matrix and 3 marks for the distance, and those 3 marks were 1 mark for having a go, method M1, and then an A1 for getting that top row correct, because that was the really tricky one, and an A1 for the rest. Sorry. So then on the next page I've done it nicely typed out just so that you can see it in case my handwriting's too scruffy. And then the question moves on and says to us, after the 3rd iteration we get these 2 matrices, and you're asked to perform the 4th iteration. So you're working from something that was given you, and we're doing the 4th iteration, so I've highlighted the row and the column 4 in the distance matrix and the column 4 in the root matrix, because those will not change during this iteration. They are fixed, so I can start off by filling in some values that I know are not going to change during this iteration. Then once I've done that, I need to look at each entry. So I'll start with 1 up here, which was 44, and I look at the highlighted values in the row and column there and add them together. 15 plus 15 is 30, which is smaller than 44, so I'm going to replace the 44 with a 30, and I'm going to put a ring round it to show myself, to remind myself that I've changed that value, because if I change a value in the distance matrix I will need to change it in the root matrix as well. But I'm going to do all the distances first. So moving along, row 1, we have a 5 and a 15 is 20, which is smaller than the 22, so I will also replace the 22 with the 20. And 25 plus 15 is 40, which is smaller than 42, so I will replace that one as well. When I look at column 5 on row 1 though, 15 plus 16 is not smaller than the 15 that was there already, so I leave the 15 where it is. And I repeat this process for the other rows. So on row 2, 15 plus 5 is 20, smaller than 22. 5 plus 5 is 10, which is smaller than the 44. Then I have an entry 20, 25 plus 5 is not smaller than 20, so I leave that as it is, and I should make sure that I put my rings around there. And on this side, 5 plus 16 is 21, which is smaller than the 23, so I'll put that one in there. Now you might notice that I've got a 30 and a 20 and a 30 and a 20, and in fact it's true to say that once we start amending these matrices they will still remain symmetric, so I can fill in some values going down here, as long as I remember that they've changed as well, from my top row and my second row, and again that's saving me a little bit of time in the exam to do that. So row 3, I get here to 40, and 25 plus 25 is not smaller than 40, so that 40 will stay. And on this side, 25 plus 16 is 41, so that entry will change. And then down here we have 30, 16 plus 16 is not smaller than 30, so that one doesn't change. And I've done the distance matrix. When it comes to filling in the root matrix, all the entries in my distance matrix that have a circle round them will now need to be altered in the distance matrix, and what I alter them to is the value that is in the highlighted column. So just because it's a 4th iteration doesn't mean they're automatically going to be 4, although many of them will be. So 1, 1, I've changed, so that is a 4, and this one becomes a 4, and this one becomes a 4, but I didn't change the 5th entry in row 1, so that remains a 5. Similarly, in the second row, I'm going to get a 4, but the entry in column 3 will remain a 3, and the entry in column 5 will now become a 4. On row 3, you will notice that the entry that is highlighted is a 2. So the first entry where I've changed the distance is going to be a 2. The second and the third were 2 already, and the 5th also needs to change, but that was a 2 already, so it hasn't changed it, but it still is consistent with my 2. The 4th row won't have changed because I haven't changed any of the distances, and the 5th row, that one stays the same, those 2 become 4s, and that one stays the same. And that's my completed 4th iteration. And if I flip over, you'll see that it's set out neatly there, and the reason it's set out neatly there is because there are no changes on the 5th iteration, and we are told that. So we're asked to use our answer to part 2 to find the shortest distance and the route from vertex 3 to vertex 1. Now, if you'd made mistakes in the previous part and your answers weren't correct, as long as you use your own table correctly, you could get the full 5 marks for this part of the question. You would not be penalised again. So looking at this, we're going from 3 here to 1 here, and we'll start with the distance matrix, and the distance from 3 to 1 is 40. So we can say distance, and then we're looking in row 3, column 1 of the distance matrix, and the distance is 40 kilometers. 2 marks for that, 1 for getting the distance of 40 and 1 for explaining where you looked for that. And that explain is very important. So it's really important that you try to explain things, but you don't need to write loads of stuff. You're fine just to write down what I've written here, row 3, column 1 of the distance matrix, and that explains that you know what you're doing. With the route, it's a little more interesting. So we're starting at vertex 3 here, and the first thing we do is we move to column 1. So we're going row 3 to column 1, and that takes us from 3 to 2. So we're now at 2, and we go from 2 to column 1, and that takes us to 4. So we've now moved from 2 to 4, and we're now at 4, and we go from 4 into column 1, that takes us to 1. So we're going row 4 to column 1, and that takes us from 4 to 1. So our actual route has taken us from 3 to 2 to 4 to 1. And again, what I've written down there classes as absolutely fine for explaining how you did it. And there were 2 marks for this part for the explanation of the rows and columns here, and 1 mark for that part. So that gives you your 5 marks altogether. Now it's a long question, so we haven't finished yet. The next thing we're being asked to do is to draw a complete network of shortest distances, not including the loops. So we've been specifically told here not to include loops. If it doesn't tell you not to include loops, you should include them. And I'm just going to draw 5 vertices I've drawn mine like this. You don't have to, as long as you have 5 vertices and you've got the right connections. It doesn't matter what it looks like visually. So using our matrix down here, which was what we had at the end of the last time, 1 to 2 has length 20, 1 to 3 has a length of 40, 1 to 4 has a length of 15, and 1 to 5 also has a length of 15. 2 to 3 that needs to be filled in, that length is 20. 2 to 4 down here, and that length is going to be 21. Is it? I'm lying. That length is going to be 5. I read the wrong thing. And 2 to 5 over here, and that's 21. Then we need to look at 3 to 4, which is 25, and 3 to 5 is 41, and finally 4 to 5 is 16. So it's not very beautiful. I'm drawing on a screen, but if yours look that good in the exam, you will get full marks for that part of the question. And then the fifth part asks us to use the nearest neighbour algorithm, starting at vertex 2. So frequently the exam questions will tell you where to start. Always read them carefully, because if you start in the wrong place, you'll be penalised. And the nearest neighbour says we start somewhere and we go to the nearest place that we haven't visited yet. So if we're starting at 2, the nearest place is going to be 4, because 2 to 4 is only 5. So I'll do that here. Now I'm doing it on the drawing. You could do it from the table if you wish. And then when I'm at 4, the next nearest place is going to be, well, not 2 because we've been there, not 3, not 5, it's actually going to be direct to number 1 up here. So next thing I'm doing is going to number 1, and you'll see that as I do this I'm writing the distances underneath so that I can simply add them up and get the length at the end. So when I get to number 1, the next nearest place we haven't visited yet is number 5. And when I get to number 5, well, I visited 1, 2 and 4, so I think I'm going to have to go to vertex 3, and that means I'm going to have to go along this long edge here. And of course this is one of the downsides of the nearest neighbour algorithm, is that being a greedy algorithm, it just works in the next step forward and never considers what it's done. So it frequently produces a solution that has a very long edge towards the end. And once I've got to 3, I need to remember, because it's a tour that I'm looking for, that I need to get back to where I started. So I have to go from 3 to 2, and that's another 20. So my nearest neighbour algorithm gives me a route that goes 2, 4, 1, 5, 3, 2, and the distance that I'm going to have to travel to do that is the sum of those numbers there, which is 96. And then we have to interpret our cycle in terms of the original diagram. So when we did the original diagram, when we began the session, we talked about interpreting your solution, and this is what you have to do. So if I use my matrices down here to help me at this point, because I can do, if I go from 2 to 4, you'll notice it's a direct route from 2 to 4. So 2 to 4 is fine. Once I'm at 4, I'll go over here. I want to go to 1, and that's also a direct route. Then when I get to 1, I want to go to 5, which is also direct. When I get to 5, I need to go to 3, but if I'm at 5 and I go to 3, column 3, that takes me to 4. So then I need to go back to 4 and go to column 3, and that takes me to 2. And then I need to go to 2 and column 3, and then I get to 3. So in actual fact, what has happened is that I've gone from 5 to 3 via 4 and 2. And then at 3, I go directly back to 2. So I've used the table to help me there with the interpretation. You could have done it from being able to see your original network. But what is important is that you get that 5 to 3 via 4 and 2. That's the actual interpretation. So for 5 marks there were, in this one, 1 mark for getting the distance, there was a mark for interpreting the route, and there was a mark for getting the initial route, 1 here, and then 1 additional mark for getting that interpretation correct. So you got 1 mark here for getting a route that had some interpretation, and 1 mark if you got the correct interpretation. And the final part says state what the algorithm has achieved. And what the algorithm has achieved is an upper bound for the travelling salesperson. So we use the nearest neighbour as a method for finding an upper bound for the travelling salesman or salesperson problem. And if you said that, that would be fine. All done. Now, this is what the examiner's report said about this particular question, and it's worth having a look at, because what this does is it highlights the common errors that people made. So it mentions the fact that people were confused between vertex 1 and 2 where the roads meet, and a lot of people made that mistake. It's not a vertex unless it's specifically got a blob and a label on it. A number of people tried to work through the whole of Floyd's algorithm, in spite of the fact that they gave you the 3rd iteration. So look carefully, don't do more work than you have to. If an iteration is given to you and you're asked to do the next one, you don't have to start from the beginning and show that what they've given you is correct. A few people made errors in the root matrix when they had to do the replacement on the 4th row. And again, in spite of being told that there were no changes for the 5th iteration, a few people insisted on doing it. You don't really have time in the exam to do this, so do use the information that you're given wisely. The other thing to note here is that you can read the distance travelled by looking at that one column, in this particular case row 3 column 1. A significant number of people seem to take the steps that match those from the root matrix, and that again takes extra time. It's not incorrect, but it just takes time. And finally, forgetting to return to the start when you do a cycle is a big problem. So if you're doing a cycle, you will go all the way around, but you must return to your starting point. And failing to interpret in the light of the original network. Again, the last part, making sure that you state something that is appropriate so that it is an upper bound or a feasible tour. Now, I've got another question here, but because these are very long, I'm not going to go through this in quite as much detail for the first few parts, because it's very similar to the previous one. And I think if you do plenty of past paper practice, you will see that the questions are pretty similar. So here, you were given a network, you were asked to complete 2 tables for iteration 4 and then find the shortest route and distance from a particular vertex to another one. And this is how it should have looked. Complete 2 tables, and you can see here the marking. So M1 is for having a go and A is for getting it right. So if you've done some of it correctly, you'll get an M and probably 1 A, and if you've done all of it correctly, you get both the A's. And in this particular case, they've given 3 marks for the distance and 3 marks for the route matrix, which is rather nice. There's your shortest route, 1 mark only. It says give the shortest route, it doesn't say write the distance. So if you wrote the distance, that's not wrong, but you wouldn't have got any extra marks for it. And then using a final distance table to produce a complete network representing shortest distances between the vertices, you will notice that this one has loops on it. And in general, as I said, you should always include the loops unless it specifically says don't put the loops on, as it did in the previous example. Then we've got nearest neighbour algorithm again. Interpret the nearest neighbour to give the Hamiltonian cycle, and then it asks us to improve on the Hamiltonian cycle by starting at one of the other vertices, and that was pretty straightforward. In fact, there's your nearest neighbour, there's the interpretation, and in fact you didn't have to do anything much for this part 4 because it's only 1 mark, so they just expected you to notice that if you started at 1 or 2 or 5 you would get a shorter route, and that's all you had to say. So it's worth looking at the allocated marks, because if it is 1 mark, it's something where you're expected to be able to do it very quickly indeed, and you don't need to show a lot of working out for that. And then part 5 we will work through, because this is a different problem to the ones we did in the first one. First of all, using the complete network of shortest distances excluding the loops, find a lower bound for the solution of the travelling salesperson problem by deleting vertex 4 and its arcs. So when we looked at the other one, we didn't do a lower bound, so this is how we generally do a lower bound. So we're going to delete vertex 4. So I'm going to put in the other vertices, but not vertex 4, and I will connect the other vertices and you can't draw most of these without having some edges crossing. The fact that the edges cross doesn't matter. So we just pretend that 4 isn't there. And what we have to do now is find a minimum connector for that. And it says you may find the minimum connector by inspection. So there's no need to actually show that you've used an algorithm. I suppose I'm probably doing it using Kruskal's, in the sense that I'm going to go from 5 to 1 because that's 3, and then the next shortest edge is 5, and the next shortest edge is 7, and that gets me a minimum connector. So my minimum connector is 5 to 1, 1 to 2, and 2 to 3. So it has a length of 15 by adding those 3 lengths together. And then in order to get the lower bound, what we do is we reconnect vertex 4 and the important thing here is using the 2 shortest edges. So you can't just repeat an edge, you need to use 2 distinct short edges to reconnect 4. So if I put 4 back in the middle there, I would use that one because that has a length of 2, and this one because that has a length of 4. So I'm using 4, 1 with a length of 2 and 4 to 2 with a length of 3, which is 5. So I can say that my lower bound is going to be the minimum connector plus the edges to reconnect vertex 4, and that means it has a length of 20. So that's the standard method for finding lower bounds. Delete one vertex, find a minimum connector for the remaining network, and then reconnect the deleted vertex with the 2 shortest edges. It seems a little weird, but that's how we do it. And down here, I've not quite written on it, 1 mark for getting a 3-arc connector and 1 mark for realizing for working out the length was 15, and another mark for reconnecting 4 with those 2 edges. The last part of this particular question, and the last question we're going to do in this session, is the route inspection problem. Given that the sum of the road lengths in the original network is 43, give a walk of minimum length which traverses every arc in the original network at least once and returns to the start. Show your methodology. So although there's only 3 marks for this, it's very important that you actually show your working out. And for route inspection, what you need to know is that it's all about the odd vertices. So we will be repeating edges that connect odd vertices, and as you should be aware, there's always going to be an even number of odd vertices. So identify those first of all, and in this particular case it's 1, 2, 3 and 5. And then the algorithm states that we have to consider all the possible pairings of those odd vertices. So we could repeat 1 and 2 and 3 and 5, and if we did, then the distance from 1 to 2 is 5, and that's via 4 here. So a lot of people would have put 6 down, but it's actually 5 going via vertex 4. And the distance from 3 to 5 is 9, so we'd have to travel an extra 14 kilometers. Or we could repeat 1 and 3 and 2 and 5. If we repeated 1 to 3, then that is 8, and 2 to 5, the shortest distance, is also going to be 8, and that's not at all obvious, is it? 2 to 4, 4 to 1 and 1 to 5. Or last of all, we could repeat 1 and 5 and 2 and 3. So 1 to 5 is 3 and 2 to 3 is 7, and that's 10. So this is the minimum distance we would have to repeat, so that's the one that we would choose. And the distance that we're going to have to travel is going to be the 43 that is given to us as the sum of the road lengths in the original network, plus the extra distance for our repeats that we need, and that's going to give us 53 kilometers. And we ought to give an example of a route. Obviously there are many different routes you could take. This isn't a unique solution by any means, but what happens is if we repeat 2 to 3 and 1 to 5, if you draw those on, it's very easy to find one, because what you've done now is you've made all the vertices even, and once they're all even, it becomes an Eulerian network, and therefore it's possible to find an Eulerian cycle. I'll give an example of a route that goes 1 to 5 to 1, then 2 to 3 to 2, then to 4 to 3 to 5 to 4 to 1. I've remembered to go back to my starting points, and I said I was going to repeat 1 and 5 and 2 and 3, so the examiner will be looking to see if he can see those, and sure enough, there's 1 to 5 repeated, and there's 2 to 3 repeated. So that ends this particular video. You can save whiteboard screens by following the instructions there, and there is our final slide, and hopefully we'll see you again for another video very soon. Good luck with the exams, and I hope you're going to be very successful.